understanding delta G0 prime and delta G of activation. In the study of enzyme kinetics, it's important to understand the difference between the overall free energy change for a reaction, usually written as delta G0 prime, and the energy of activation, usually written as delta G dagger. This video discusses this difference and also addresses the usual but different castings of these equations for these two free energies and the related equilibrium and rate constants. Okay, so let's get started. First, we'll draw an axis system, and we'll label it with energy on the y-axis and reaction coordinate on the x-axis. And we'll draw the substrate energy, and then we'll draw the product energy and the activation barrier for the reaction, and label the activation barrier peak as X dagger. That's our transition state. And then we'll label the diagram to show the overall delta G, delta G0 prime, as well as the activation energy for the forward reaction, written as delta G dagger. And now we'll write the two equations that relate delta G and delta G dagger to the diagram that we've just created. One is delta G0 prime equals minus RT ln of KEQ. The other is K equals AE to the minus delta G dagger over RT. But what's the relationship of these two equations to each other? It's worth looking at these two equations and realizing that there is a similarity of form here. Both equations contain a delta G of some sort. Both of them include the constant R and the temperature T, and one contains an equilibrium constant, whereas the other contains a rate constant. What's the relationship of these two to each other mathematically? Let's take a look. First of all, we can write the first one, delta G0 prime equals minus RT ln of KEQ, and we can rearrange this by dividing through by minus RT and setting that, of course, equal to ln of KEQ. And now we can take the exponential of each side of this equation, and that will give us KEQ equals e to the minus delta G0 prime over RT. And this bears a striking similarity to the other equation that we described above, the equation for the rate constant in terms of the activation energy for the reaction. So let's write that down. K equals AE to the minus delta G dagger over RT. We can take the natural logarithm of both sides of this equation and write ln of K equals ln of A minus delta G dagger over RT. And we can rearrange this equation so that we can write delta G dagger equals minus RT ln of K. And this is very similar to the form of the equation that we wrote earlier for delta G0. The difference, of course, is that there's an additional term, minus RT ln of A. Now, A is a frequency factor for the reaction, and if we assume a frequency factor of 1, meaning that every collision results in a reaction, then we can simply say that the natural log of 1 is 0, and then delta G dagger becomes minus RT ln of K, and this has the exact same form as the equation that we've always written for delta G0 prime, minus RT times a natural logarithm of a constant. This time it's a rate constant. In the case of the overall delta G, it's an equilibrium constant. The difference lies in the fact that for the activation energy, we have only considered the forward reaction. If we considered both the forward and reverse reactions, we would end up with a ratio of rate constants, which would essentially give us the equilibrium constant for the reaction. We'll discuss that at another point.